Hey folks, Todd Coburn here with your Aerospace Structures series. This video is on analysis of reinforced concrete. We're going to be using the Aerospace Strength Handbook, Volume 1, which provides a simple, straightforward, detailed procedure for this kind of analysis. In order to do this, we're going to have to use the same exact nomenclature in the text. So if we have a section, as we see here, this particular section is reinforced with three steel rods, as we can see, and it's 6 inches deep, 4 inches wide, and these rods are located 1 inch from the bottom. We're going to need to define the coordinate system the same way, which means we're going to define the y reference axis as we see right here. Okay? From the top, acting downward. That's critical for the way the equations are developed. We're going to use the same nomenclature as the text, which means we're going to call the height of the beam H. We're going to call the width of the beam B. Okay? We're going to call this dimension here from the bottom of the beam to the steel rods E. The diameter of the rods, we're going to call the steel rods, is going to be D. As we said, our Y bar is from the top. If our original section looked like this, and it did, what we're going to do is we're going to apply a typical concrete analysis procedure, which basically assumes that the concrete, which is really lousy in tension, is completely cracked. And in its cracked state, it can carry nothing but compression. That's what makes this problem challenging for the average analyst. So since we're idealizing it as being completely cracked, that means only the compression part, the concrete that's in compression, can carry load. Now we can see that this moment is causing compression on the top. So the top will be in compression and some depth of the concrete. So this little piece here is the concrete that's in compression, where this is our neutral axis. Okay? We're going to idealize using our simple multiple material method. We're going to take the steel area and we're going to idealize it with an equivalent width of steel. So it's infinitesimally tall and it has the exact same area as the steel rods. Now, we're going to take this nomenclature that we used above and we're going to augment that. We called that H, the depth, B was the width, E was the distance from the bottom to the center of the rods. We're going to also define from the top to the center of the rods. We're going to call that H, and we're going to call the distance from the top of the beam to the neutral axis, we're going to call that H prime. Okay? And once again, our Y is going to be calculated from the top of the beam downward. Now, and then, now because this assumption, now what this means is, if we look at the side of this, so if this is the end of the beam, let's do that with black. If this is the end of the beam carrying this moment, basically everything above the neutral axis is going to be assumed to have a constant stress. It's going to carry a constant stress of the concrete, and then at the center of the rods, we're going to assume the steel stress. And this is the way this is reacted. And as we could see before, our section goes all the way down to here. Our actual section goes from here to here. But our assumed section, actually, let me clean that up a little bit. Let me re-sketch this section. Since that's not completely clear, we can say, okay, our section, our beam goes from here to down here, looking at the side of it, but what we're idealizing it is a section that's like this deep, and a point area right here where the rods are. So we've got this piece for concrete and this part for steel. The concrete is in compression, the steel is in tension. Okay, that is our assumed. So we get this is going to be the effective force in the concrete, and this is the effective force in the steel. And using this assumption and approach, that is going to allow us to analyze this. Now, the next step, once we have understood the nomenclature, we're going to, now normally you have to solve, because we don't know where the neutral axis is, where the point of zero stress is, if you idealize this with the assumed stress distribution that I'm showing right here, and we can call this the assumed stress distribution, right? And this is all over here is our nomenclature, okay? Our next step is to find the neutral axis. Now, you need to solve the quadratic equation to do this, but I give you a nice simple formula, and what this will do is tell us what H prime is for our section, and it actually simplifies down from our handbook. We've got negative N steel, A steel, plus or minus the square root of N steel squared A steel squared plus 2N steel BHA steel. And all that is in the square root. And then on the bottom, this is over B. Okay, that's our first step, to find out what is this H prime dimension that we showed down in our nomenclature. That is giving us the position of the neutral axis from the top of the beam. Now, if we plug in our equations, we see a few things here. We see, so N steel is actually the ratio of the modulus of steel to the modulus of concrete. Now, let's say that our modulus of steel and our modulus of concrete, let's say our steel has a modulus of, about 30 million, right? 30 MSI, 30 million PSI. Our concrete has a modulus of about 3 MSI, 3 million PSI. That means our ratio, 30 to 3, is 10, right? Our N steel is 10. We then can calculate our area of the total steel, and that is going to be the number of rods that we have times the area of those rods. So that's D over 2. D is the diameter of those rods squared, right? And this is going to give us, we have 3 rods, and our diameter is 0.375. So our area of the steel is going to be 0.33134 inches squared. Okay? So now let's see, what else do we need in our equation? We've got B already is 4, and we are now ready, it looks like that's everything we need, to plug in all these values into H prime, and we can find out where the value is. Now you get a plus and a minus, but only one of them is meaningful. We're going to get a 2.16659 inches, and we're going to get a negative number, which is complete nonsense, so we will ignore that. And we will take this as our position of the neutral axis. Now, once we have that, we can then go to the next step and calculate the y-bar. Well, the y-bar, which is the distance from the top to the neutral axis, that is just our H prime. We already know where that is. And we already know what the area of the steel is. And now what we need to do is calculate, we're ready to calculate the moment of inertia of our transformed section. We're going to use the same approach that we cover in our video on multiple materials, where once we have the N, which is the ratio of the stiffness of each element to the reference element, we're going to actually use a modified width of each element, which gives us a moment of inertia. It's not the moment of inertia, it's a factored value by N, which in our multiple material video I call it the moment of inertia, or the moment of inertia, because it's not the moment of inertia, but we need it. So we're going to calculate I sub n. I sub n is defined in your handbook. It's already calculated for you, so it's 1/3 the width times the H prime value. Don't confuse the different H's. We have H, capital H, lowercase h, and H prime. That's cubed, plus N steel times area steel times H minus H prime squared. If you solve that for this beam, you will find that the moment of inertia for this beam is 40.1610 inches to the fourth. Okay? Now that we have that, we can calculate our stress. If we wanted to also calculate the area of the total section, we would need to use the area, which is the area factored by our factor. So that's going to be BH prime plus N steel, A steel, which is going to give us let's see, the total area of this guy is 11.980 inches squared. So we have our moment of inertia and we have our area. And our stress now at any point is simply P over the area times N of whatever material it is you want the stress in at that point minus the moment that we're given times the y bar minus yi. The y bar of the section, which is where our CG is, minus the y of the point, all referencing back to the upper surface, divided by the moment of inertia times N of whatever that material is. Now, typically, we're only going to want two stresses. We're going to want the stress in the concrete, and we're going to want the stress at the steel. So we will plug in two values. We'll plug in the top of the concrete, and we will plug in the bottom of the steel. So if we do that, then we plug into our equation. Now, there's no axial load in this case, in which case we can calculate our stress in the concrete at the top and our stress in the steel. Our stress on the steel for this particular case is going to be 42.33 KSI, and our stress in the concrete is going to be minus 3.237 KSI. And once again, we're going to need to make sure that we multiply by those factors when we do that. This is how you calculate and then if we were solving our problem, we would then box our answers. Minus 3.2, this would be 4 KSI in the concrete, and the steel will be 40.3 KSI. And that would be how we get our stresses. That is how you analyze a reinforced concrete section. It's pretty straightforward. This process will work. You can use different numbers of rods. You can have a different configuration. It basically is using a single row of rods. You would have to tweak the analysis slightly in order to handle a double row. This is not pre-stressed concrete. That may add another complication. We're not going to cover that in this class, maybe in a later video. Got it? Enjoy.